Well, this is the final session for this section of the course, the clinical trials element. We will have a class on Friday where, since I haven't heard anything else, we'll be going through last year's past paper. So it'll be a revision section, revision for this section of the course. Okay, and then after reading week, Tim will then start in the same time slots, giving the survival analysis elements of the course. Okay. As I said before, it seemed to make sense to have the revision on this bit now rather than Tim start with just one session before reading week. So we brought that forward. His revision session, I think he's intending to have it actually in January rather than before Christmas. Okay, but you'll need to check with him about that. Okay, so this final section is the second half of chapter 11. It's talking about logistic regression, logistic type modelling, as an alternative way of handling binary data. This is much more flexible. It we'll see how it ties up with some of the things we looked at, calculating relative risks and odds ratios. This is used very widely, not just in medical statistics. It is also an example of more general types of regression modelling, which themselves are used very, very widely. We only cover it in detail, so many of you will see this in other courses as well, but it is just a taste for people who don't see this material anywhere else, to the way you can broaden regression modelling out much more widely than you will have seen if you were doing a second year course. Okay, so if you're not doing much statistics and you haven't done the extended linear models topics, you may well not see anymore, but this should serve to explain to you how regression type modelling can be extended to other types of data structure. So the data in question here are binary data. So by that we mean our response Y is either a 1 or a 0. So a success or failure, alive or dead, whatever. Logistic modelling is to be preferred from some of those very simple count-based type things, because we can put in, as we can in most regression things, we can include other covariates. It's not just dead or alive according to whether treated or not just summarising everything down into simple two-way tables. We can put in extra covariates there. It's readily available, but it's interesting, the maths doesn't work out quite as neatly as ordinary regression, so it's not quite available everywhere. So these are the courses where you would see more about it if you're taking those, but if not, this should be interesting for you. I'm not going to do it at all formally here, okay, because those people who need to know how to do it formally will see it elsewhere. We're going to concentrate on the interpretation and how we can use it or see it, how we see it used in a medical setting, essentially. I think you will see a little bit more with Tim as well, some very similar ideas in other types of regression modelling that he does for his specialist type of data later on in this semester. So, the basic idea is we want to assess the effect of multiple variables, one of which will be treatment, but not only treatment, multiple variables on the probability of being a success. Okay? We want to set up basically like ordinary regression, because we know that's what that's for, looking at the effects of multiple variables on the sum response. So we want it to be like that because we know how to do that. This is the setup that we usually have. We say, on average, our response is given by some linear combination of the values of various, here we've got P different predictors or covariates, and we estimate from the data of suitable values for the coefficients, betas, so that on average they're predicting Y well. Okay, you might see it written down without the expectation on this side but with an error on this side, or there are different ways to phrase it, but essentially that's what we're doing. And the idea there is, I can see here I've been, well, okay, we can make predictions at some new X set of X values. We can then use the estimated hatted versions of the betas to predict Y's. Okay, I've been, throughout this section, I haven't been very precise about the terminology and things. Here I've assumed the X vector, which I haven't defined, to be all the X's plus an indicator, so that I can collapse all the betas, including beta naught, down into a single variable. But I think I haven't been entirely consistent over that in the notes, whether the beta naught is included or whether it's separate. I think I've sometimes written it one way and sometimes the other. Now, if you think about it, what we're going to want to do is to say that some linear combination of X values, and our covariates, we're not saying anything about the covariates that they have to be just binary things themselves. I mean, with the treatment, yes, maybe that is binary, but with all the other things, it's quite likely we'll want to put in people's ages or values of some biochemical markers in the blood or something, and we're not reliably going to find that if we just let our X's be general, that our estimated value of the betas are such that the number we would get out of that combination would either be 0 or 1. It's going to be quite a hefty problem to try and find a set of betas that will always do for whatever our X's are. So it's not feasible to say we can have a linear combination coming up to just being a value 0 or 1. So don't focus on predicting the actual 0 or 1 itself. Focus on something else, functions of the response. Okay, so the first one we might do, and this is what I already alluded to, we really want to know the probability of being a 1. Okay, so is it feasible that we could get some linear combination of betas and X's giving us a probability for being a 1? Well, it is feasible, but it's still going to be a little bit difficult because it's a probability, so it's going to be in 0, 1. Okay, so that means we're going to, when we try to find the values of the betas that best fit, give us a best fitting model of this type, we're going to have to do some constrained optimization. And I'm guessing you've perhaps done things like Lagrange multipliers and things like that. Yes, but they're a bit fiddly and they're not terribly well suited necessarily to all types of constraint and so on. So that's a bit of a faff. So instead of saying, okay, we'll work with that, let's look at some other possible functions. Here's a function that we were talking about before, the odds. Okay, so that's probability y is a 1 divided by probability y is not a 1, which in this case is that y is a 0, since there are only the two possibilities. So that's the odds of being a success. And that is still constrained, but only much less so. So it's only constrained on one side. Okay, so that might be a better thing to do. But even better would be to take the log of that. And again, we're talking of natural logarithms. Here it doesn't, in some senses it doesn't matter, it's just a shifting, but for definiteness we always talk about natural logarithms, and it works with lots of probability models, of course, because lots of them have got exponential terms in. So if we look at the log of the odds of success, which is given this special name, the logit, okay, if we look at that, that is an unconstrained function. So we don't have to do anything special in our choice of the betas to make sure it's going to give us, when we put them back into our weighted linear combination, that they're going to give us suitable values for predicting success or failure. via going through this. So what we actually do then, oh sorry, I'm just introducing some extra terminology here. The x's in this case, we've already just generally referred to them as variables or factors. I've used the term covariates quite a lot, but in medical setting they're often called prognostic variables or factors, because this is about predicting the course of a disease. You know, where your diagnosis is deciding what disease you've got, your prognosis is looking at how things are going to map out for you in the future. So they are the hope is, of course, that these are factors that will predict whether or not you're a success at the end of the course of treatment. So, and as I said, I have been a bit loose about the expectations or errors, but basically now what we're saying is on the left hand side, instead of just y, we've got the logit of y here. So we write it as that, and here I can see I've written it in a different way. Because I've only defined from x1 up to xp, I've kept the beta naught separate. So the beta just goes from beta 1 to beta p, and beta naught is kept separate. So in textbooks, I could have collapsed all of those down to be a vector beta if I'd extended the x to have a 1 at the beginning. Is everybody happy with the two ways of writing it? Yeah, you know what I mean? Yeah? Okay, so you'll see both in the literature. It doesn't really matter, you obviously just need to look in context. And sometimes the data anyway will have been centred up in some way that makes the use of a freestanding constant not necessary. But you can see now this, I mean, if we're happy with what's on the left-hand side, the right-hand side's just like any other regression model. So the x's can be of any type. They could be continuous, discrete, or dummy. And we'll look at some examples of all of those in a bit. Obviously, it's all very well saying, oh yes, we can look at this funny function of it, and that has a nice way, you know, it's going to be sensible to express that as a linear combination of prognostic factors. But actually, we were interested in the probability of being a success, not the log odds of being a success. But if you just back transform, so taking exponentials of both sides, okay, that's that one. And if you rewrite this, and it's very often given the notation theta, okay? So you'll often see that in the literature. If you know that, of course, because this is 1 minus theta and this is theta, so if you just cross-multiply and muddle things together, you will find out that if theta over 1 minus theta equals this, then theta equals this. Okay, so the exponential of the predictor over 1 plus that exponential is the way to actually get the probability, and this will be in 0, 1 as it should be. Okay, so this is the logistic regression model. It has pretty much the same sort of properties as you would expect. So in particular, all that messing around with what's on the left-hand side hasn't altered how you interpret the sign of the coefficient. So beta j being positive doesn't just mean the log odds of success are positive, increasing as xj increases. It actually maps through to the success itself. Okay, so doing the back transforming doesn't change the direction. So if that coefficient is positive, it's saying, yes, the two things are positively correlated, where the two things in question are the x variable and the probability of success. Okay, so it's got exactly the opposite of the thing here. If it's positive, they're going in tandem, both up, both down, or if it's negative, they're at odds, so cross things. Just looking at how we do it, how we do the interpretation once we've got values for these values, for these parameters and so on. One of the things we said we were going to do is that we were going to look at treatment. That's our core aim in a clinical trial. We want, all right, we know there are lots of other covariates, and what we really want to do is allow for those all being potentially different, and then after that say, is there an effective treatment? Okay, so in the notes actually for this chapter, I think here I was more consistent, and I used x1 to be the treatment variable all the way through. Okay, so x2 to xp are other things. We'll see an example of them being other things in a minute, but x1 is the treatment. So x1, if you code x1 as 0 for being on placebo and 1 for being on treatment, okay, so that the models will be like this. And what you're doing is so if you're on the placebo, you don't have any x1 term, that's gone, so here. Whereas here, you get beta 1 times 1 if you're on the treatment. So you can see what that is it's just a shift of size beta 1 in the constant term in the model, okay? So what that's telling us is if you've coded it up in this way with the same thing here, beta being positive means the odds of success are greater in the treated group. Okay. Beta being negative, odds of success are greater in the placebo group. Depends what you mean by a success. Okay, so very easy interpretation. But so you can just look at the betas themselves. It's also sometimes helpful to go back to things we looked at before, odds ratios. That's particularly useful if the factor, the explanatory factor, the possible prognostic factor, is itself binary. So are you on treatment or not? Are you male or female? You know, those sorts of things. Now this often is called the relative risk, but it isn't. I think I have in the past deliberately put this in questions to ask you to calculate the relative risk, and what I'm expecting you to say is we can't exactly do that, but can give you an odds ratio, and they might be similar. Depends on the rarity of the events. But what we mean by that for the odds ratio, so this is the odds ratio of disease, so it's the odds ratio for disease on treatment compared with placebo. So we've got two binary factors going on here. So here we've got the ratio with the dividing line. So this is the odds ratio of disease when you are on treatment. So it's the odds ratio of disease because it's comparing that your y value is 1, you've got the disease, to your y value being 0, okay, 1 minus that. It's the odds ratio of disease when you're on treatment, because I've said your x1 value is 1, and it's the ratio of that whole thing when your x value is 1 to when your x1 value is 0, okay? And if you go through just writing out all the equations, you will see that that is just the exponential of beta 1. Okay, so the coefficient that you get in your regression model, if you look at the exponential of that, that will give you the odds ratio of treatment, of disease on treatment as compared to being on placebo. So that is another way of describing the effect of being on the treatment. Yeah? So often we might not just quote beta 1, we might quote the exponential of beta 1. But it does it for other binary factors, or you can also do an odds ratio like this, not just with a single x value here, but you could specify two levels of any covariate. So you could ask, what's the difference between somebody who's 40 and somebody who's 50? Okay, that's a continuous covariate, but you could ask at two different settings, calculate the ratio of the odds under those two settings. Or you could do multiple collections of variables. So I think we've had in the exam, we've asked you to compare a 40-year-old smoking man with a 20-year-old non-smoking woman or something. So you can do any combinations just substituting in. And if you look at it, what it tells you in the end is comparing people with that collection of characteristics to the people with that collection of characteristics. Okay. There, obviously, you'd have to substitute out the whole equations and see quite what cancelled out. But that's what it's going to be telling you. It's going to be telling you about how the odds of having the disease change under those two collections of patient characteristics. So there's some examples of doing all these things coming up in a minute. Just to say, what does set it apart from ordinary regression is that because of the complications of having just a binary fundamental response and then looking at that function of it, you don't get closed form values for the beta hat. So ordinarily you'd have a thing where you said this thing. That's how you don't get just a little formula like that in the case of logistic regression. Nonetheless, you can use a maximum likelihood type approach. The likelihood is just of this form because it's just a product of a whole load of Bernoulli terms, because if the theta, and this is the theta as I defined it before, the probability of being a success, then you've got that, and each time you count 1 if you were a success, so your y is 1, and you count 1 for the non-successes if you're a failure. So it works right. That is the likelihood. Obviously, there are some, binomial coefficients out the front, essentially, but it's proportional to that. But the maximisation of that has to be done numerically. In this case, you don't get just a neat formula like that, which sometimes limits its use on very big problems. But it's quite... So you have to use iterative methods, but there's a kind of like a Newton-Raphson type of doing it. But for you, all it means is nobody's ever going to ask you to do one of those by hand. Just pressing the button to get one of these is no more difficult than pressing the button to get an ordinary regression equation. Okay, so that's what will be going on behind the scenes, but by the time it comes out to you, it looks pretty much the same. So we have the whole same performance about trying to fit a model, decide whether certain terms should be in it or not, and assessing, so that you assess whether a variable should be a regression, and there are two ways you can do it. Either you can look at the significance of the coefficients, or you can look at the model sums of squares with it in and without it in. So you have both the equivalent types of things here. Some slightly different terminology, but it's not actually any different. So the first thing is you can test, is my beta j equal to 0? So you take your estimated value of beta j, the coefficient for the xj variable. You take off 0 because that's your null hypothesized value, which of course does very little. And then you divide it by standard error, square root of its variance. That thing, obviously, it's a bit more fiddly to work out what that is. Again, in ordinary regression, there's a neat formula involving a lot of x-x terms. Here, it's more complicated, but you can get numerical values for these things out. Strictly speaking, obviously, that's an estimated standard error, so we might think of t-tests, but everything's all a bit approximate anyway, and you've only got it with numerical methods and so on. So we never bother to go for a fancy t thing. We always just go with standard normal percentage points. So we're looking at this and we're saying, is it outside plus or minus 1.96, plus or minus 2, that sort of thing. Okay, that's one way you can do it, which is called the partial Z test, and it's kind of called partial because there can be issues about in unbalanced data about which order you put the variables in, and you're looking at this one on its own. Sometimes you're conditioning, sometimes you're not, and that sort of thing. The other way you can do it is via a likelihood ratio test, which is the thing that normally you would be using the ANOVA command to compare a full model and a reduced model. You do the same sort of thing here. In this situation, that sort of sums of squares equivalent is actually called a deviance. But the way you get it, it compares, and it is twice the log likelihood under the full model minus the log likelihood under the reduced model, where the reduction is to say that beta j is 0, so that xj variable has no effect. Okay, so that's the two variables. Instead of counting the sum of squares, that's a special case of this, where you actually look at the maximised log likelihood, which is more generally called the deviance. So if you look at twice the difference of the modulus of those of maximised values of the log likelihood, then there's a very far-reaching theorem which tells you that those will be chi-squared 1. Okay, so that's saying if this looks surprising against a chi-squared 1, then it makes a difference whether you use the full model or the reduced model. If it makes a difference, doing the reduction is not a sensible thing to do. If it doesn't make much difference, you might as well get away with a simpler model and just miss out variable xj. So that's the same reasoning as you would ordinarily use when choosing what model to fit. So for instance, something we sometimes might ask people to do here is give you the R output, you know, this model and this model. Say which model you prefer, so you can, you know, if you're given these values, you can make that choice yourself. Here I just did the case where I was putting one variable to 0, but it could be that you drop several variables simultaneously, and then that would, if you drop, say, 3 variables, this will be a chi-squared 3, because you can add up chi-squareds if they're independent. Okay, so that's most often used. You know, usually with regression you do the usual thing, which is to drop one variable at a time, check in as you go. But sometimes if you've used dummy variables and you need several dummy variables to code up a set of different options, then you might find yourself, you usually drop all of those. You either have them all in or all out. Okay, so you might see things where you've dropped 2 things at once. So for instance, if you'd got smoking at, you know, light, medium and heavy or something like that, smoker, and you code those up with dummy variables, so you need 2 dummy variables to code for 3 levels of smoking, and you might say, I just want to drop all those out at once, think smoking has no effect at all. Okay. So there are these 2 ways of doing it. Either is fine, and there have been, as I say, certainly past exam questions with this sort of question on there doing that. So here's an example where we see quite a lot of these things, and it's all it's entirely a classic one, this one. So it's looking at a particular drug on heart disease. Okay, so these are men who've got high levels of cholesterol in this trial. The prognostic factors, obviously there's the drug, but the other factors that might determine how your heart disease progressed: age, smoking, the father's sort of history. if you've ever been asked things at the doctor, they always ask you things along these lines. Blood pressure and cholesterol level. Okay, so this is an example of how these might be coded up. So again, I've kept it that X1 is the treatment that we're actually interested in. And these other things, notice we put them in afterwards. So typically this will be the first one, these will be afterwards, because typically what we're interested in doing is saying, after I've adjusted for all those other things, does treatment have an effect still? Okay, and in a balanced design, it doesn't matter too much what order things have been put in, but in an unbalanced situation, you can have order effects and so on. So it's good to stick to a sort of standard setting. So what we've got here is, are you on placebo or the active drug? Age has been logged, presumably to sort of focus in attention on small differences in a particular age range, rather than, because heart disease isn't a disease of the young, is it? So probably to bring some separation to older ages. I've logged that. So smoking here has been coded very simply non-smoker or smoker. The family history of health in this, in general, is just a simple code of, at whatever age you are, is your father still alive or not? Okay, so they often ask more detailed questions. Has anybody in your family had, you know, one of these types of disease or things like that? But some sort of family history to try and get at your genetic predisposition, presumably, is very often included in medical studies. Blood pressure in standard units and cholesterol in standard units. Okay, so that's the data. The response, it's been coded up as Y as being a success, is being that the patient has heart disease. Okay, not what you might think, but anyway, that's the way it's coded, and that does fit in with what we had before, I think. So this is what you would get out from R, or anything else that you did it in. Variable, constant term, it might be reported there, it might be reported at the top. The value for the estimate, and either you might be given its standard error and have to work out the Z value yourself, or given the Z value and you can work out the standard error if you need it for something else, which you might. We'll have a look at that in a minute. So if you, sometimes you'll even get the p-values for doing the test that we've got here. But as we said before, what we're doing is checking whether these are outside plus or minus 1.96. It would be for a 95% or a 5% test, 95% confidence interval type setting. Even if we go to 1%, which takes us out to plus or minus 2.58, in fact, actually we can see all of these numbers are much larger than that. Okay. Interestingly, the treatment ones, the smallest of these, but all of these things seem to be important. And you interpret them the obvious way, so focusing first on the treatment effect, because that's our main thing. It's significant, so this is the partial Z test. The p-value is less than 1% because our value of minus, whatever it was, minus 0.32, with whatever standard error we've got, gives us a Z value of minus 2.9, so it's less than 2.58, minus 2.58. So it's significant. It's negative, so that means the probability of being a success, which in this case was getting heart disease, was smaller on the treatment than placebo. So that's what we want. Okay. If your success is a nasty thing, you want it to be less on treatment. So the treatment is beneficial, seems to be working. If we calculate, say, an odds ratio for having heart disease, comparing the active and placebo versions of the drug. That will be the same as looking at the exponential of beta 1. So the exponential of that is 0.73, and that's less than 1. Of course, it's an odds ratio. Well, it itself is a ratio, so we look at it being less than 1. So what we can say, so this is a way that these are often interpreted, because see, this number is 0.73. So this is 0.27 lower. The odds of having heart disease are 0.27, the complement of this, lower on clofibrate than on placebo. So it's lowered your odds. So people would very quickly switch into saying lowering your risk of getting heart disease. So they slightly loosely use the terms interchangeably. Okay, but it's lower on the drug after allowing for the other factors. Okay, if you want to give some sort of confidence intervals, which we often do in statistics, you'd need to work out what the standard error of beta 1, because we had this value, the z value, should be estimate over its standard error, so cross multiplying the standard error is that over that. You may well be given it in the R output. I've forgotten what R gives you. Different packages give you different things, but if you can work out the standard error for beta 1 in this case, and then we get approximate 95% confidence interval by estimate plus or minus 1.96 or 2, really doesn't matter. Okay, everything's a bit approximate, times that standard error. So that tells us this is for beta 1, that's a confidence interval. And you might, because people like talking about on this scale, the X beta scale, it's a bit like we were doing with the odds ratios earlier on. We work on the log scale and then we back transform to the scale we're wanting to talk on. So X of beta 1 has 95% limits X of whatever the two endpoints were, X of that and X of that. So you might see people saying the reduction, because we know we've said it's below 1, so we know it is a reduction in odds of heart disease, are somewhere between 10 and 42%. Okay, the complement of this and the complement of that. So you might see the increase in it due to smoking is somewhere between this and this, or the reduction in it if you're on this drug is somewhere between this and this. Okay, so all of these are different ways to describe the effect. I mean, you know, they all work by the algebra just carries through. You just have to think what way seems most natural or seems most natural to your audience. Some people are very happy thinking about odds. Other people want to talk about just the probabilities themselves and work with the whole equation or whatever. That was assessing the treatment effect. We can do similar things with any of the prognostic factors. All of them are significant because they were all weren't they all positive. Apart from that, they were all positive, so they were all bigger than 2.58. They've all got positive coefficients. So just doing it, actually, they're all in the obvious direction, by which I mean probability of heart disease increases with increasing age, increases when you smoke as opposed to don't smoke. If you have poorer heredity, so if your father has died, it's more likely that you will have heart disease if you've got high blood pressure and high cholesterol. So everything's going in the expected direction. Okay? And you can just report those, or you can report X of things. So if you do a similar calculation to the one I've just shown you, here's another one so you can check for yourself that you're doing it right. So this is the increase in odds of getting heart disease for smokers. That is presumably as opposed to non-smokers. is somewhere between 80 and 193%. Okay, but that's an increase in odds, which I don't find it a very easy scale to work on, but some people like it. So you will see it's just a matter of putting in the values into the equation in a suitable place. If you can remember the shortcuts, yes, it's x of this or that or the other if you want, but it's, you know, you may just want to go through all the algebra yourself again. You could do exactly the same as you could in any other regression. So, for instance, it is very likely that the variables don't interact, affect things just on their own, that there are interactions between them. You do put in interaction terms in exactly the same way as you would anywhere else by looking at creating a new variable, which is the product of something else. So most often in these settings, you wouldn't consider all the variables, all possible interactions. For a start, you might consider, does the treatment behave differently for different types of patients? So you would focus at least first on treatment by patient characteristics. Okay, so if you didn't have enough data to fit a very elaborate model, you might focus on those ones. So if you wanted to have, in that example that we've got, an interaction between treatment and log age, which was what was coded x2, create a new variable, call it x7, because we had 1 to 6 before. Literally, you multiply together the things. So x7 will be the same as x2 if you're on treatment, but it will be 0 if you're on the placebo, because x1 was just 0 or 1. Okay. And if you put it in the model, it's the obvious thing, the thing we've got on this side. If you're on placebo, you will just not have anything here with x1, whereas if you're on, but you'll also have nothing to do with x7. Okay, so you'll have no x1 and no x7. Whereas if you're on treatment, you will have had the beta-1 effect of treatment, but the effect of x2 will be described by a new coefficient, which is the sum of the other one plus the interaction with treatment. And so what you've got here is this is a new coefficient that's talking about the it changes the dependence on age. It's different for people who are on treatment from people who are not on treatment. So it's just having a different slope in your dependence diagram. Okay. And of course it extends, you can have anything you like in there, triple interactions or anything else. So this is exactly ordinary. There's nothing here that is remotely different from any other variable. It's any other regression setting. It's just making the point that you might want to do that here, and it is the only thing that's a bit special is typically you might want to look at whether the treatment acts differently on different types of patient as opposed to any other interaction you can think of. Here's another sort of additional variable that we might look at, and this is earlier on when we talked about combining trials with the very simple Mantel-Heinzel type of meta-analysis, and we said there was perhaps a better way to do it that was coming up. Well, this is the example of doing that same type of exercise using logistic regression. So the idea is that we want to recognise that our data has come from multiple different centres or multiple different small trials. We're putting them together. And we might want to recognise that some of the effects might be in common throughout all the trials, but there might be some things that are trial specific. And we're we can say what we believe to be true, we can investigate different things and rule out certain sorts of possibility, although you have to be a bit careful because they're not necessarily always nested, but they might be. Depends what you're comparing. So in this example, the way I've set it up is I've said the beta 1s should be the same, reflecting that saying the effect of the treatment should be the same, because beta 1's the coefficient for x1, the treatment. Beta 1, so the treatment effect is the same everywhere, but something is a bit different in trial J. That means the typical levels of the response, are higher or lower, or the probability of being a success are higher or lower, because you're simply in that trial centre. Okay, so what we've said. So if you've got 3 clinics, which was the example we had before, I think, code them, use 2 dummy variables to code them, so that's one possible coding. So this is the model. You have overall effect, beta 1 being your effect of the treatment, and then beta 2 and beta 3 giving the dependence on these dummy variables, okay? And that will be fitting, in effect, fitting this model for clinic 1, just the very simple thing. But in clinic 2, you've shifted your mean level by a certain amount, but the beta 1 is kept the same. In clinic 3, again, the beta 1 is the same, so the same dependence on treatment, but different intercepts for the logit, depending on which clinic you're in. And so when you've got estimates for beta 0, beta 1, beta 2 and beta 3, you can actually do all the obvious inference. You can test whether the clinics are in fact different. You can test whether there is a treatment effect, whether it's going in the right direction, all that sort of stuff. Okay, so that's just an example of how you could do what we talked about earlier, but rather better. Because of course this, you can, as well as having those, you can still have all the other prognostic factors on the end in every clinic. Okay, so much more sophisticated than a Mantel-Heinzel, where you just, well, you're making the same recognition. There might be a difference between the clinics, but you're not actually doing anything to model it in any way. And that's just the end of that example. Okay, so that just summarises the chapter. Okay.